So we were doing isomerism in coordination compounds, isomerism, structural isomers, and stereoisomers. Structural isomers have different groups and bonds, and stereoisomers are same group but different 3D arrangements in space. That's what we had seen, and we were about to see that what are the different types of structural isomers we are having and how to draw them. Okay, structural isomers in the coordination compounds are very easy to understand and they can be understood by their names. Okay, that's what we have discussed in the previous class. Any doubts with respect to the previous class or your NCERT problems? Okay, just you can stop me anytime, you can ask me any number of times. Okay, so we were about to start ionization isomers. Okay, ionization isomers, as the name indicate, that they have same formula, but they give different ions when put into water or aqueous medium, or different ions upon ionization. That is called ionization. So, Jesslyn, ionization isomers, for example, I have given two examples in the previous class. These are the most common example. In every book, you will find this example in all the books. Okay, and this is about the two complexes of cobalt, right? So we can also try to name them. So the first one is pentamine chloride cobalt 3 sulfate, and the second one is pentamine sulfato cobalt 3 chloride. Okay, and it is clearly visible that when you put them in the water, they will ionize and they will give different ions. So Jasleen, can you tell me, Marwa, can you tell me how to know which ions are separating after putting in water? What is the method? Can you tell me the method? I can give you some hint. You can find, you might have done some school practicals. Okay, that techniques you can use here. Is it clear or not? So look here, cobalt is +3, Marwa, right? And you have Cl minus. Okay, so +3 -1. Okay, that is going to give you +2, and that is balanced by -2. Similarly, +3 -2, the square bracket will carry +1 charge, and that is counterbalanced by Cl minus. Okay, so these two are ionization isomers. Why they are called as ionization isomers? Because you can see very well that when you put them in the water, they will give different ions. Is it clear or not?
Yes, sir.
So the left one is going to give you sulfate and the right one is going to give you chloride. So how can you make out whether which one is giving us sulfate and which one is giving us chloride? What's the technique? Jaslene, can you tell me? The technique is by adding BaCl2 and AgNO3. Barium chloride is going to form the precipitate with sulfate as BaS4. Got it?
Yes, sir.
And BaS4 is white PPT. So this one is going to give you, the first one is going to give you the PPT with BaSO4, BaCl2. The second one is not going to give you PPT with BaCl2, it is going to give you the white precipitate of silver chloride with silver nitrate. But if you put barium chloride, no precipitate is obtained in the right one. Barium chloride is going to precipitate the sulfate and silver nitrate is going to give precipitate with the chloride. Okay, so this I hope is clear to all of you. Okay, these are ionization isomers. And how we have made them? Or these ionization isomers are made by exchanging the sulfate with the chloride. Okay, you exchange the ions and the ligands, and with that you can get the ionization isomer. Got it? So let us do some problems. So write the formula for ionization isomers of the following compounds. So how can we draw the ionization isomers of this compound? PtCl2 NH3 whole twice Br2. How to draw the ionization isomers? What's the trick? Any idea? These are the common questions, okay, which we get, and we can easily draw the ionization isomers. I told you the trick by exchanging the ion with the ligand. Okay, if you exchange the ion with the ligand, you are going to have the ionization isomers being formed. And what are the ions? It is the Br minus. There are two Br minus. You can see outside the square bracket on the right hand side, and there are two chloride ligands, chlorido ligands inside the square bracket. So you can exchange them. Okay, and that's how you can make the ionization isomer. So how we are going to do it, Jaslene, Mara, tell me quickly. I hope I'm audible to all of you.
Yes, sir.
Okay, so PT, BR, CL. I will exchange one BR with one CL. NH3, NH3 whole twice. CL, BR outside the square bracket, and or one more option which I can follow is I can I can send both the Br minus inside the coordination sphere and exchange them with the Cl minus. So Pt Br2 NH3 whole twice Cl2. Got it? So you can have it in this manner. So total you will have three isomers. Is it clear or not?
Yes, sir.
They are ionization isomer, and once you put them in water, you will see that they are going to give different ions. The first one is going to give 2 Br minus. The second one is going to give 1 mole of Cl minus and 1 mole of Br minus, and the third one is going to give you 2 moles of Cl minus, right? So that is a way by which you can have the ionization isomers. Let's do one more problem for the ionization isomers. One, the total number of ionization isomers of the following compound. What is this OX means? It means oxalator. Got it? So you need to find the total number of ionization isomers. So how can we do that? Just tell me quickly. Oxalator, the hint is oxalator is which kind of ligand? Is it a monodentate or a bidentate? So can you tell me, Aisha, Marwa, Jaslene, can you tell me oxalator is what kind of ligand? Is it monodentate, bidentate, tridentate? That is very important to solve this problem. We need to know what kind of ligand oxalator is. Okay. Oxalator,
Bidentate.
yes, exactly. It is a bidentate. So why am I asking all of a sudden? Okay, this is -2 and it was having this structure. So when it connects to the metal, it connects by giving two lone pairs. Okay, that we know. Okay. So if it and the coordination number of the cobalt is 6. You can see there are 6 ligands, 2 bromido and 4 NH3. And if you are taking the oxalator inside the square bracket, you need to exchange one oxalator, which is a bidentate ligand, with 2 bromido. Got it? Is it clear? Because bromido is monodentate. Okay. I mean to say that one bidentate ligand is exchanged with 2 monodentate ligands. Is it clear or not? So the next isomer is CO, OX, NH3, 4. I can't exchange NH3 here. Okay, Br2, right? So that's an important thing. I hope this is clear to all of you. Got it? Any doubts on this?
No, sir.
Okay, so this is, there are two ionization isomers. Okay, so ionization isomers, as the name indicate, Aisha, just we were discussing some of the examples of ionization isomers. Okay, so we were discussing that ionization isomers, how they are formed. Okay, so they are formed when the ions are exchanged with the ligand. Okay, you can see that in this case, in the previous example, Br is exchanged with Cl, one Br with one Cl, because Br was also monodentate, Cl was also monodentate. And the example which we are doing right now, one oxalator is exchanged with two bromido ligand, because oxalator is a bidentate and bromido is a monodentate. So this I hope is clear to all of you. Okay. Very simple. Okay. Coordination number, uh, you can be have 4 or 6 coordination numbers. Okay. In it. Now let's move to the another isomerism, and that is solvate. Okay, first we have covered the ionization isomer name. The name also can suggest ionization isomer. Solvate isomer. Okay. What's the other name for solvate isomerism? Aisha, am I audible? And how the solvate isomers are formed? So, Jesslyn, what's the other name for the solvate isomerism? Marwa, what's the other name for the solvate isomerism?
Ionization isomerism.
No, ionization is different. Ionization, you have different ions. Okay, when you put it in water like this one. In this, the sulfate was ionized, in this chloride was. So the formula was same. In So these were ionization isomers. Okay. In solvate or hydrate isomerism, if it is water, that is high. If water is involved, that is hydrate. Or common name is solvate isomerism. Okay. So solvate isomerism, these are the complexes having same formula, but they have different molecule, the water of crystallizations. Different number of water of crystallization molecules. So let's have this some molecules. Okay. So there are different formulas for it. Okay. This is, I will remove it. Okay. This different formulas I can write for this one. The primary valency for the chromium is 3. Okay. Plus 3 charge. And the secondary valency is 6. So chromium H2O whole 6 and Cl3. Water molecules are satisfying the secondary valency, the coordination number, forming 6 covalent bonds, and the Cl minus are satisfying the charge. Okay, got it? Now, let's say if we bring one Cl inside the coordination sphere, and we have no other option but to exchange water molecule, water ligand. Okay, H2O5, Cl2, and that water molecule will come out and will stay as water of crystallization. Okay, if it is water molecule coming out, that is called hydrate isomer. It has the same formula but different water of crystallization. Is it clear or not?
Yes.
Yes, sir.
Suppose which is the next hydrate isomer of the above molecule. Next, how can we do that? We can do one more time what we have done, right? So now we have Cr, Cl2, Okay, we have taken two chlorido inside the square bracket and two water molecules outside. H2O4 coordination number is going to remain 6 only. Okay, so now only 4 water molecules can stay inside. One Cl has remained outside. Clear?
Yes.
Then that will become neutral if it is totally inside. So that we will not consider. So these are the three molecules which have the same formula, but actually they are giving different water of crystallization. Water of crystallization, what are they? They are actually the salts. Copper sulfate you have seen, okay. The formula also you know. Copper sulfate is that blue colored compound is CuS SO4.5H2. So these water molecules are known as water of crystallization. And in the coordination compounds, if there are water ligands and if you exchange them with the ions, okay, if you exchange them with the ions, the water molecule is going to come out and stay as water of crystallization. So such isomers will be called by the name of hydrate isomer if it is water, or the general name is solvate isomer. Is it clear or not?
Yes.
I hope everybody understood this. Except what's the last molecule we are not going to consider because that molecule will become neutral. Okay. So this is water. Similarly, like water, you can exchange the NH3 ligands also. But if it is NH3, okay, if it is NH3, then it is called solvate isomerism, right? Then it is called solvate isomerism if it is NH3. So let me write the examples of NH3 also. Same example we can carry forward here also with NH3, but this, the hydrate you are not going to use. That is very important. So these are solvate isomers. Okay. Here hydrate I cannot use because it is not the water molecule which is being exchanged. Right? Clear? Now we are going to move on to the linkage isomerism. Jesslyn, Marwa, Aisha, tell me what are linkage isomers? What are linkage isomers? And what is the criteria of ligands we need to have to show link it? Yeah. Yeah, Marwa?
Um, Same ligands.
Pardon?
Same ligands that bind the central atom to different donors.
Yeah, actually, yeah, linkage is it is because of the ambidentate ligands. Okay. So what are ambidentate ligands? Ambidentate ligand are the monodentate ligands which can form bond with the metal ion by two different ways. Okay, by connecting themselves to a same metal atom or ion in two different ways. They are called ambidentate. They are not bidentate, they are monodentate only. Right, Marwa? So examples of ambidentate, and we have seen in alkyl aryl halide also that ambidentate nucleophiles. Okay, CN or NC, NO2 or ON. Okay, so you have ONO. Normally, you represent it in this way. The arrow the from a particular atom indicates the bond. Okay, or you can represent it in this way. Got it? So basically, this is the first one is nitrito O and the second one is nitrito N. Is it clear? They have the same name nowadays and their name is represented after the name you write the capital letter of representing the donor atom to which they are connected to the central metal atom or ion in a complex. Okay, so the ligand is same ONO or NO2. It can bind itself to the metal ion in two different ways. Okay, is it clear? So that's what the difference is only. So this type of isomerism can only be shown by the complexes having containing at least one ambidentate ligand. At least one ambidentate ligand should be there, right? For example, if you have how can I make the linkage isomer? Jaslina, am I audible?
Yes, sir.
So how can we make the linkage isomer of this complex? I can write the same metal, cobalt. Rest of the ligands are kept as it is. They are not changed. NH3 5 and I will change only the ambidentate ligand, the connection of ambidentate ligand. That I can change. Okay. So now this is NO2. Is it clear? The overall formula has remained same, but the connection, the way in which, or the linkage between the ambidentate ligand and the metal ion, that has changed. That's why it is called linkage isomers. So ligands like SCN, NCS, NO2 and ONO, OCN and NCO, they can show the linkage isomer. Why they can, how they can show? Because they have at least one ambidentate ligand. And that is the criteria for the linkage isomer. Is it clear? So how we are going to draw? So let me ask you a question. Which of the following there are some complexes which look very similar. Okay. And student may get confused that they may also may start thinking that they may also exhibit or show the linkage isomer. So which of the following? Yes, Jasleen, your answer is correct. Aisha and Marwa. What could be the right answer? Yeah, Marwa. It is option. Option. Yeah, it is option C, right? Okay. NO3 and ONO2 look same, but NO3 is monodentate ligand. It is the oxygen only which can donate the pair of electron. Is that clear? So OCN and NCN. Yeah. Jasleen, is it clear or not?
Yes, sir.
Any doubts?
No, sir.
Aisha and Marwa, I hope this is clear. OCN and NCU. OCN is like this. This is called cynato. Cynato O.
Sir, thiosulfate is also
Yeah.
an ambident ligand.
Yeah, thiosulfate is also an ambidentate ligand. Yeah, I'm coming to that. Because let me write the structure. Sulfato and thiosulfato, what's the difference? So this is the most common answer, okay? Normally, if it is a single correct, you are going to choose option C, right? Nitrate and don't get confused with nitrate and nitrito. Is that clear? ONO and NO3 minus. ONO is the nitrogen lone pair can give and O can give, right? Is it clear? Now, let's talk about the thiosulfato and sulfato. Okay, sulfate is this one. Can it be ambidentate? Or normally what we do is there are two oxygen with O minus and two oxygen with double bond, right? So can it be ambidentate? No. It is because it is only the oxygen which is carrying the negative charges. Okay, sulfur doesn't carry any lone pair. Is it clear? Sulfur, all the valencies are satisfied. You can see that all the electrons, sulfur is having 6 valence electron. Okay, and all the 6 bonds are there, right? So sulfur doesn't have any lone pair, sulfur will not care. Is that clear? What about thiosulfate? Thiosulfato, if you try to recall, as the name indicate, sulfate and thiosulfate, you replace oxygen by S. Got it? Is it clear?
Yes.
And when you draw the resonance structures, okay, in this case, if you draw the resonance structures, where the minus is going to come in? The minus is going to come in on another oxygen, this oxygen, or this oxygen, okay? It is going to circulate between 4 oxygen. But suppose if I do the resonance in this case, where the minus is going to come in, okay? It is going to come on oxygen, right? So this could also act like an ambidentate ligand where the oxygen can give or the sulfur can give. But normally, why I have told you that if it is a single correct, go for option C. If it is multi correct, okay, go for option A and C both. Normally, thiosulfate actually binds itself through sulfur. Okay, because sulfur is more nucleophilic, a better electron donor. So normally, if there is only one option to this question, assume thiosulfate will connect through sulfur only. But if it is actually asking about the detailed analysis, the thiosulfate also is an ambidentate ligand, and there are two names for the thiosulfato. This is the upper one is thiosulfato O, and the lower one is thiosulfato S. Is it clear or not? Any doubts in this? Jaslene, Aisha, Marwa?
No, sir.
But so normally thiosulfato S is the most common. Most common form is thiosulfato S. Okay. But if they ask you in detail where this thiosulfato is the only option and other options are not matching, take the thiosulfato, right? Or if it is more than one correct, then A and C will become the answer. If it is single correct, assume thiosulfato most common form is connecting through S only, right? Is it clear? So most common form is thiosulfato S, right? So these are some of the examples of linkage isomerism. Total number of linkage isomers. Can you tell me? This is total number of linkage isomers. You need to write the formulas. How can we do that? If we look at the square bracket, there are two chlorido. They can be only monodentate, not ambidentate. But there are two thiocyanato. So this is where we need to look at. Is it clear? So total linkage isomers. Will be equal to 3. Got it? Is that clear? Aisha, Marwa, Justine, is it clear or not?
Yes.
Sir, can you explain again?
SCN or NCS you can do, okay? Only linkage we have considered. Next is coordination isomers. What is coordination isomer? Who can tell me the definition? What are coordination isomers? Any idea? Coordination isomers are just like the ionization isomers, but be very careful. They are different. Okay, normally students make mistake and they actually consider both same. Okay, but there is a difference. What is the difference? Who is going to tell me? Aisha, Marwa, tell me quickly. Jesslyn, coordination isomers. Any idea what are coordination isomers? What are coordination isomers? So wherever you have both cation and anion are complex ions, okay, with the square bracket, first of all, such compounds only can show coordination isomer. Let's say, suppose if you have a cationic complex, okay, and you have the anion also as complex. Is that clear?
Yes.
So you have the ligands, okay, and you are, in order to form the coordination isomer, you exchange these ligands with each other. Got it? You exchange the ligand of the cationic part, square bracket with the cation into the square bracket with the anion. This is not ionization isomers. Ionization isomers, you have only one square bracket while the other part is normal simple anion. Okay, this is known as simple anion. And this is known as complex anion, okay, or complex cation. So if you have both the parts as complex, so how can you make the isomers? You can make the isomers by exchanging the ligands between the two coordination spheres. That's the method only we need to adopt. Okay, while exchanging, if you are exchanging monodentate ligand, on the other side also one monodentate ligand should be exchanged. But if you are exchanging a bidentate ligand, you need to have two monodentate ligand. Okay. So let's see a few examples. Just tell me what are we going to exchange with and whom?
The NH3 and the Cl will exchange ions.
NH3 is going to exchange with Cl. Okay, one by one we are going to do that. So how many coordination isomers we can get?
4.
How many coordination isomers? Total number of coordination isomers we can make. How many are there? Understood my question?
2.
How many? Two. One more we can do. So I have taken one chloride on the left hand side and one NaC on the right hand side, right? What about other isomers? Jaslene, Marwa, Aisha, tell me. Can we exchange two chloride with two amine ligands? Can we do this? Aisha, what do you think?
Yes. No, we cannot do.
Hmm.
Sir, no.
Why? Why no? Yeah, your answer is okay, but what is the reason?
It's identical.
Jaslene, could you help me out to understand the reason? Marwa, can't I exchange two chlorido with two NH3 or three chlorido with three NH3? That's what I've done, right? And all the four chlorido with all the four NH3. But we can't do that. Why? What's the reason? Jaslene, would you like to add anything? Marwa, Aisha?
Because the overall charge is
Yes, this will become neutral.
usually.
It is going to become neutral. So if it is neutral, no point of writing them side by side, okay? It has become neutral. But what about the other two which are written below it? What happened to those? Why we are not taking? They are not neutral. They are still that each square bracket is charged. Can you see it? So why we are not taking them? What's the reason? Yeah, Justine, what's the answer? Why we are not taking the third one and the fourth one in our options? The reason is we have already taken them. Look here. This one and this one are same. Just they are written like this. Got it? Is it clear?
Yes, sir.
They are written in opposite manner. Okay. First the cation is written, then anion. In the second one, anion and then cation are mentioned. So it is just the same. Okay. And if it is just the same, we are not going to consider as it as two different isomers. Same is the case with the first one and the last one. Look. PTCl4 and 4NH3. Okay. If you try to swap them, they are just same. PTCl4 I have written first. Okay. And PTNH3 whole 4 I have written afterwards. So it is not going to become a new compound. The cation and anion still are the same. So this one and this one, they are same. So it is just a repetition. So total how many different unique isomers we are going to have? Just 2. Got it? Is it clear to everyone? Any doubts in this? So we need to exchange the ligands. Okay. We need to be very careful that they should not become neutral. Okay, one thing is this, that they should not become neutral. Another thing is there should not be the repetition of cases. That also you need to keep in mind. Is it clear? Because sometimes what happens is you see that there are repetitions happening. Okay, and you see after the middle case, you see that the isomers getting repeated again and again. Okay, so now let me give you another isomer. PTNH3 4 and PT oxalato whole twice. How many isomers we can have? Just remember one thing, that it should not become neutral. Another thing is, if you are exchanging oxalato, you need to exchange 2 NH3 with 1 oxalato. Got it? Because oxalato is a bidentate and NH3 is a monodentate again. So just try to do it. How many coordination isomers are we going to get? Aisha, Jaslyn, tell me quickly. How many are we going to get? Coordination isomer. 2. And how am I going to make it? If I exchange one oxalate, look what has happened. Platinum is +2, right? And this is +2. Oxalate is -2. There are 2 oxalato. This is -2. So this is +2. Okay. The cation is +2 charge and the anion is -2 charge. If I bring one oxalato, I need to shift to NH3 because oxalato is a bidentate. Got it? Is it clear? But should I consider it in my counting or not? Tell me. Look what has happened. PT is +2. Oxalato is -2. This whole complex has become neutral. And if it is neutral, you are not going to write the cation. It has a cation and an anion. Okay, so this case actually was ruled out because it became neutral. Okay, you need to reject the neutral complexes because you need to have a complex cation and complex anion. That thing you should must keep in mind. And in the second case, if you bring two oxalato, you need to take the all the four NSA on the other side. That will just be the same as that of the same as this original isomers. Is it clear? So that is also not going to show any. There was only one option, but that option actually was rejected because it was neutral. Okay. So regarding this, we need to be careful. Okay, it should not become neutral. Is it clear to all of you? Any doubts in this? If there are no doubts, we can proceed to optical isomers. Optical and geometrical isomerism, stereoisomer. Stereoisomerism in coordination compounds. So how will you define a stereoisomerism? Aisha, Marwa, tell me quickly. All of you know it very well. Just leave it. Stereoisomers.
It's the same chemical formula but different arrangement.
Different three-dimensional arrangement. Okay. Same molecular formula, same groups, but those groups differ only with respect to the three-dimensional arrangement in space. And there are two broad categories of stereoisomers. What are the two broad categories? They are geometrical and optical isomers. Okay, geometrical isomers are what? There are two different types of geometrical isomers. They are known as cis and trans, and as the name indicates, cis means on the same side, trans means on the opposite side. Okay, but there are other names also. Okay. Optical isomers. What are optical isomers? Marwa, Jasleen, Aisha, tell me. What are optical isomers? They have the same formula, they have different arrangement of group, three-dimensional arrangement, okay, and they differ with respect to the optical rotation of their optical rotation also. So you check the optical rotation of this compound in a polarimeter. One isomer can be dextrorotatory, another isomer can be levorotatory, right? So that we can discuss in detail. First, we need to look at the geometrical isomerism. Regarding the geometrical isomerism, I need to first know that suppose if you have a square planar complex, if you have a tetrahedral complex, an octahedral complex. Got it? Square planar is like this. This is square planar. The four ligands are in the plane pointing towards the corner of a square, and the four ligands are like this. I'm not writing the ligands just to keep the formula simple. I'm just drawing the arrangements. Square planar, tetrahedral, octahedral. Now tell me, which complex can show geometrical isomerism? Or where there is no possibility of showing geometrical isomerism? What all complexes are capable of showing geometrical isomerism?
So they should have ligands. Ligands.
Pardon?
There should be at least two different ligands.
Yeah. Formula I will write, but there are certain options which we can clearly rule out. Okay, this will not show geometrical isomerism. Yeah, once you get into the formula, then it depends upon the ligands. But there are certain arrangements where you can directly rule out, okay, this arrangement cannot show geometrical isomerism, and that is tetrahedral. You can have octahedral complex showing geometrical isomerism. Optical isomerism, square planar will not show. Okay, and tetrahedral can show, octahedral can show depending upon the nature of the ligand, and you are absolutely correct. Geometrical isomer, you need to have two ligands, two same of one kind, two of another kind, right? But even if you have different ligand, you cannot have geometrical isomerism in tetrahedral complexes. Is this clear to you? Aisha, Marwa, Jaslin, tell me.
Yes, sir.
So what's the reason why tetrahedral complex will not show geometrical isomerism, even with different ligands? Aisha, can you tell me something about it? Why the tetrahedral complex cannot show? Marwa, what's the reason?
Yes, sir.
It's because of 3D structure.
It is?
Because of the 3D structure.
Yeah, 3D structure. Yes, exactly. It's something related to that. Marwa, what you were telling? Why tetrahedral complex will not show geometrical isomers? What's the reason? In geometrical isomerism, if you try to look at the detail, you need to have complexes, you need to have cis arrangement of the ligands or trans. Okay. And cis means same side and trans means opposite side. Got it? that you know. Though we will take the examples. In tetrahedral complexes, there is nothing same or opposite. They are all same. All bond angles are same. All bond angles are same. No two positions can be considered cis, no two can be considered trans. In square planar, you can consider cis and trans. Got it? So that's why tetrahedral will not show geometrical isomerism. Do keep this in mind. Octahedral can show. So geometrical isomerism in tetrahedral complexes, square planar complexes. All of these are square planar. Platinum is +2, Cl is -1, so +1 charge. So all of these are square planar. That you can see that they are square planar. And now I have taken different ligand. I have not taken all four same ligands because that is not going to show the isomerism, geometrical isomerism. Got it? So what all complexes can show exhibit geometrical isomerism? Cis and trans. You need to have two ligands of one kind and two ligands of another kind. And those two ligands of one kind are on the same side. Okay, you will call it as cis. If they are on the opposite side at 180°, you will call it as trans. Got it? This is the basic idea. The most fundamental questions. Is that clear or not? Aisha, Jaslin, Marwa, tell me quickly. So this cannot show geometrical isomerism because there are just one ligand of different kind. One ligand, and this also say the same criteria. One ligand of is different, the rest all are same. Okay, how we are going to represent it? So Aisha, why it cannot be cis trans? And Jaslin, why the first one cannot show cis trans? What's the reason? Jaslin, Aisha, Marwa, tell me. No geometrical isomerism, no geometrical isomerism. Why? What's the reason, Aisha? No, it's not because it is unsymmetrical. There are two, this can show, okay. Two ligands of one kind and at least two of one kind and two of another kind. So in this case, I can show you that suppose if you have Cl, Cl, NH3, NH3, got it? This is going to be the cis. Cis in Latin means same side. The Cl, you can see there are two Cl, you can compare them that they are on the same side. Okay, at 90 degree. Aisha, is it clear? Jaslin, are you getting my point or not? And
Yes, sir.
Marwa, suppose if I draw them like this, what is the angle between the two chlorido What is the angle between the two amine ligands? It is 180. They are exactly opposite to each other. Got it? Exactly opposite. So that is trans. So at least two ligand of one kind, two ligand of another kind, then it can exhibit geometrical isomerism. But this is just one. Rest three are all same. So whom do you compare to be on the same side or on the opposite side? Got the point? Is it clear? So which one will you call it as same side? Which one will you call it as on the opposite side? You need to have two ligands for the sake of at least two ligands. If three ligands are same, okay, NH3 is same on the cis, NH3 is trans also, so it should not be considered, okay. Marwa, are you getting? Jaslin, Aisha?
Yes, sir.
This can show at least two different ligands should be there, at least, or just one ligand different from rest of the other ligand will not fulfill the purpose. Same is the case here also. So this is not going to exhibit, this is not going to exhibit, this can show, and this can also show. You can compare F and Cl, you can compare F and Br, Br and Cl, Br and I, Cl and I. Okay, to be on the same side or opposite side. So your homework is you need to try this question. This is very, very important. Okay. And in the next class, let me know how many geometrical isomers it is having. It is a square planar complex with all four ligands different from each other. Got it? So you need to draw them, just compare their angles and make sure you don't make them twice or miss some of the isomers. Got it? So we are good. This is a very important case, and this isomer we have already seen. It is used in the medicine where we have seen it in the previous class. What is the common name of this cis isomer? Can you tell me? This is cisplatin. Remember, it is used as an anti-cancer drug. We have seen. And the right one is transplatin, that is not used. Cisplatin is used as an anti-cancer drug. Okay. So let's discuss this one in the next class. Okay, and we are going to move with other examples of isomers in the next class.